I'm very happy to be here to present this work by, as I wrote here, Bérczi and Bérczi-Kirwan about Green-Griffith-Long conjecture and Kobayashi conjecture for hypersurfaces with polynomial bound on the degree. So just before starting, let me warn you that I am not a specialist of non-reductive GIT theory, so I won't be able to explain you all the details of the proof. But hopefully, I will at least be able to explain you how the spaces, these spaces by Bérczi-Kirwan are constructed, and convince you that in the end, you are, the strategy that was introduced by Erwan yesterday can be applied to these non-reductive GIT quotients. So maybe let me start by recalling, maybe do a quick review of the strategy, which is based on the use of jet spaces. So strategy to prove, say, Green-Griffith-Long conjecture for hypersurfaces, and it will imply, as Eric said, the Kobayashi conjecture in a second time. So let me recall a few things about jet differentials, jet spaces. So pick X complex projective manifold. Well, projective is not necessary for the time being. So complex manifold, say. I will choose an integer, which will be the order of jet spaces we are considering. And now we have the spaces that we call typically JKX. Oh, sorry. So what we call JKX, so it's as a set, it's the set of kth Taylor expansions of germs of curves, starting from the origin in C and going to X. And this space admits natural projection to X, so pick a germ of curve, or a kth Taylor expansion of a germ of curves. So typically we denote it that way. F would be a germ of curve and we truncate it at order k. And we can, of course, send it to its value at 0. So this gives a space which is fibered above X as well, it's fibered in affine spaces, where n is, of course, the dimension of X. But let me warn you that it is not a vector space, a vector bundle, because the change of coordinates are not linear when you look at the way you write linear change, coordinate changes on the fibers are not linear. So it's not a vector bundle. Okay, so once you have this space, you can, so let me call pi k the projection. You can look at the algebra of coordinates, say, on JKX. So formally, you can push forward the structural sheaf of this scheme, JKX, and you get an algebra on X, which we call the algebra of Green-Griffith jet differentials. So it's a graded algebra. That's why I'm putting a bullet here. I will say more about that in a minute. And we call it, well, I will denote it that way. So algebra of Green-Griffith. So Erwan explained yesterday how we can express the sections of this algebra in terms of coordinates. I won't do that right away. That will appear later in the talk. But of course, if you pick coordinates on X, you have a way of writing these the sections of these algebra. But for the time being, let me just give a few more details about that. So if we fix an integer m, then we get what we call the Green-Griffith jet space Green-Griffith. This time it's a vector bundle of differential equation, well, maybe vector bundle of Green-Griffith jet differential equations of order k and degree. So I'm thinking, no, maybe it's a good time still to give a few more details about that. So if I pick coordinates on X, so I pick an open subset in X with coordinates Z1, Zn, say. Then I have coordinates on the fibers on that space, which are given by the derivatives of these coordinates Zi. So jk x restricted to u has coordinates. Well, of course, on the base, you still have these coordinates, so z1, zn. But on the vertical fibers, you also have the zi derivative, say, p times, with I between 1 and n, and p between 1 and k. So that's why you have C and K as 5. These are given by this coordinate. And the sections of the Green-Griffith jet vector bundles of jet differentials over U are generated, well, can be written as so you can see them as differential equations that you can apply to curves arriving in U. So if I will pick, say, a germ of curve arriving in U, and then to write the expression of the section, so let me pick a section on U. Then, as I said, you can apply P to F, and it will be expressed as a sum of monomials, say, in these coordinates. Of course, you have to apply them to F. So you have Fy prime to some power. Let me write it L11 until the first derivative of the nth coordinate of F. Let me put an exponent L1n. And you go all the way until the kth derivative of the coordinates of F. So Fik, let me call the exponent Lk1, until Fn derivative k times and kn. And here you have to put some coefficients depending on all the L's applied to it. And you sum over the all possible choices of L's with the following, well, you want differential equation of degree m, so you have this restriction to the L's you are considering. Okay, so this is just to fix the ideas. Sections of these vector bundles are written this way. And now, if you recall what Kirwan explained yesterday, if you want to prove Green-Griffith line for, say, the general hypersurface of degree d, it suffices to find a suitable section of that vector bundle. So let me call that proposition or theorem. So it's the consequence of the strategy of slanted vector fields. So if one manages to prove the following, so for some integer d, so there will be some restriction, but I will not maybe write them. So for some integer d, for the hypersurface it's not necessary to assume generic here. So, say for all smooth hypersurface, we managed to prove that the H0 over the hypersurface of the Green-Griffith jet differential at order n and degree m, so for some m, I will just going to write non-zero. Then the conclusion in a minute I will write is that we are able to prove Green-Griffith length for XD, for generic XD in Pn+1. But of course that is not enough. We have to add an additional vanishing on these sections at order depending on m here. And here we have a bound which is, so if you use Darhondo's work, for example, you get a linear bound here to put in that slot. So suppose you manage to prove that. Then I'm going to say Green-Griffith length holds for generic XD in Pn+1. And more precisely, the Green-Griffith length locus of XZ is different from XD. So this set which is defined via jets and which contains all Untitled curves is different from it. All right, so what we want to do is to prove this non-vanishing. So, strategy to prove the non-vanishing. This. So, it's been known for some time that we have associated to any complex manifold X, we have jet spaces, which are somehow compact versions of these, projective versions of these, and tautological line bundles on them, whose sections give you this. So I'm going to say, find the jet space. So projective variety, which I'm going to call, maybe there is a small conflict of notation here. Yeah. Okay, so bear with me for a second. This does not denote a hypersurface of degree k, but it denotes what I will call a kth jet space above X. Kth jet space, I'm going to say projective. All right. So find such a projective jet space for any k, say, dominating every projective manifold, and on it, some tautological line bundle. So typically it will be an orbifold line bundle. I'm just going to write that for completeness. Whose sections give you sections of these algebra. So let me call that IK again, such that if you push down these sections, you get Green-Griffith jet differentials. So that's the first step. And the second step, well, if you want to ensure that this equation star is true here, if you want to have this non-vanishing, you want to ask that the OK1 minus this section on the base, well, is at least effective. So here, I suppose X is a hypersurface for writing this second step. So you want that to be effective, but in the usual strategy, we ask more. We ask that it is big. Actually, the way we prove that it is big, well, we obtain bigness for free with the strategy of holomorphic Morse inequalities that I'm going to explain tomorrow. Okay, maybe just right here. Sorry.
What did you mean by a projected kth jet space?
Okay. So I mean that at least I want to have a projective morphism. So I'm going to write that here. My K is projective. And orally, I will not write that down, but just to convince you that it exists typically. So if you care only about Green-Griffith jet differential, what you can do is simply to projectivize this algebra. Just to write that here. Projectivize the Green-Griffith algebra. Then you get a projective space, projective morphism towards X, that we typically call the Green-Griffith jet space, and which is none other than the quotient of jkx minus the zero section, quotiented by C star. So there is a C star action. I'm going to talk about that in a minute. There is a natural C star action on jkx given by reparametrization of the kth Taylor expansions. And if you quotient jkx minus its zero section, minus the set of all zero jets, then you get, after quotient, some projective morphism towards X, and which is this projectivized bundle. And there is a tautological line bundle on it. So it's an orbifold line bundle because typically these are singular spaces. So a way of seeing them is to say that they are actually the Riemann-Ford stacks, orbifold in whatever sense you want. But that's why it's not strictly speaking a standard line bundle, but not majorisms. All right, and I'm just going to say that in our inventionist paper, Bérczi-Kirwan construct spaces like that, satisfying both requirements. Such that, well, first of all, we have this inclusion, but more precisely, their image fall inside the locus of what we call invariant jet differentials. I'm going to give more details about these invariant jet differentials in a minute. But it is a subalgebra of the Green-Griffith jet differentials. And for the second point, well, for instead prove that two holes if they take a degree which is polynomial, so larger than some universal constant times n to the power 5. And so that's how they get Green-Griffith length for general hypersurfaces with a polynomial degree. Okay, so that's for the general strategy. And now let me give more details about this, actually, this notion of invariant jet differentials. So when I say invariant, I mean invariant under the action of some group, namely the reparametrization group. All right. So let me introduce that group then. Here, all right. So for the K I have fixed, the order of jet differential, we can define a group, an algebraic group, which I will denote here GK. This is, so it goes by many other names. So maybe I will also write a diff K, C0. So it is simply the kth Taylor expansions of germs of maps going from the origin in C to itself, such that we have non-vanishing for the first derivative. So germs of diffeomorphism from C0 to itself, from the germs of C at 0 to itself, truncated at order k. Okay, maybe I will not write on this board because this blocks the... Okay, so we can define this group. Let me be maybe a little bit more explicit about how we can write elements of it. So GK is simply the set of all phi t, which you can write alpha t plus alpha 1t plus alpha 2t squared over 2 factorial, etc., until alpha k t to the power k divided by k factorial with alpha 1 different from 0. Okay, so these are dimension k linear algebraic groups, and they have an optional action. GK acts on JKX via reparametrization. So if I take psi in GK and germ Fk at some point of x, then I can make at psi on F simply by taking the kth order Taylor expansion of F composed with psi. Okay, so why do we care about this group actually? Well, simply because if you study hyperbolicity questions, you want to look at holomorphic maps from C to your manifold. And typically we want to prove that these maps don't exist. Or maybe there are only a few of them. But to study this kind of question, we don't really care about the parameterization of the map, but simply about, say, its image. And one thing we usually do, if we have a map from C to X, is to consider, say, its kth lift. So R1 yesterday draw a similar diagram like that. And as I said, this kth lift completely depends on the parameterization of the map. But if you want to study the non-existence of such maps, for example, you can perfectly forget about the parameterization here and also there. And so it means that the more relevant geometric object would rather be the quotient. So you would have a projection like that, and what would be very interesting is rather this map rather than that map. So this seems to be more relevant somehow geometric object. Okay, but the problem is that maybe you have already convinced yourself that this group GK is not reductive. So indeed, you can actually write the Levy exact sequence. So if you have an element of GK, you can project it to C star simply by taking its derivative at 0. And you have a kernel, which I will, in these notes, in these lectures, write as UK, like that, a bold UK, which is the unipotent radical of GK. Just say already, it's the unipotent radical, and it's the set of Taylor expansion that start with T, rather than alpha 1T. All right, and so this is unipotent. This UK is unipotent because, and introduce some notation here. You have the descending derived sequence. So in the end, you would have UK, which I will also rewrite as UK K, like that. And it has a normal subgroup all the way down to last group. Sorry, I need to write one maybe. All the way down to a last group, UKK, where I denote by UK or L like that, the set of Taylor expansions which start only at degree L after the first step. Alpha J, Tj, J factorial. And you can convince yourself that if you take the successive quotients, you get abelian groups, which are actually C with the additive law, generated by this element set. All right, so you have a non-reductive group and you want to take a quotient. So that's how non-reductive GIT appears in the picture. And my goal until the end of this talk will be to explain to you how their space, their non-reductive GIT quotient, is constructed. And before doing that, I'm going to explain that there is at least a locus on JK where things are very good. Well, this quotient has a meaning as a geometric quotient. Namely, this is the locus of regular jets. So let me define this space JK reg, which is inside the space JKX, well, the set of K jets where the first derivative is non-zero. Then claim, proposition. If you want to quotient this subset, which is a Zariski open subset in JKX, by the reparameterization group, you can do it very well with the geometric quotient. By this, I mean, how do you say that orally? I mean simply a quotient which is locally on the base principal bundle with a structure group G. So fiber-wise, you have a product, but not fiber-wise, but over the base on small open subsets, you have a product writing JK reg as GM times its quotient. So how do we prove that? And I will give you the idea, and that will permit to introduce some invariants that will also appear in the construction of this space constructed by Bérczi-Kirwan. So the idea is as follows. So put coordinates, I will do that in local coordinates, take Z1, Zn coordinates on X. Well then, you can write, so maybe start that way, JKX, so it's a bundle over OX, and vertically it has the coordinates Zi derivated P times. So allow me to write things that way. It's a relative spec above X of some algebra generated by the derivatives of the Zj. Okay, so if you want to be really formal, you simply replace X by spec of some A, of some ring, and you put that ring here. All right, and now if you want to look at the regular jets, what do? Well, you want to say that this F prime is non-zero, so this will define some conditions on that spec, and in the end what you end up doing is simply localizing this spectra at the coordinates Zj prime, and you take the union for G going from 1 to A. And then in this union you have all the regular jets. Okay, let me denote this relative spectrum by Vj. So it's the union of n affine charts, which are spectra of these rings. And now I claim that Gk, the group Gk, has a geometric quotient on each of these charts. And more precisely, on each of these charts, you can write the quotient. Well, you can write the space Vj as a product between Gk and the quotient. So, why is that so? To explain that, I'm going to draw this picture. So, I'm going to explain this with V1, just to simplify. So, take V1. I claim that in V1 there is some section, which I will call sigma 1, which crosses all the orbits of UK at exactly one point. And this section is simply given by the jets, where all higher derivatives in the Z1 coordinates are 0. So why is that so? So pick, say, a jet here, Fk, and write it as, say, f of t equal to z1 of t, zn of t. So how do you find the point which is here? The point in the same orbit, such that you have all the coordinates, all the derivatives in z1 that are 0. Well, simply, you reparameterize f of t by the z1 coordinate. You can do that because you are in the chart where z1 prime of t is different from 0 at the origin. So you are perfectly allowed to use z1 as a reparameterization and inverse the z1 coordinate that way. So if you do that, you get z1 or z1 minus 1 t, and all the way up to zn. And on the first coordinates, of course, you get t, and in the other one, you get zj or z1 minus 1 of t. And this is the point, which I will call gk, which lies in that space sigma. You have taken your point here, you have shifted it by this uk, even gk, sorry, here, to get a point inside this sigma. So now write things carefully, and you will end up proving that V1 is isomorphic to this sigma 1 times gk. Okay, so now we have at least a geometric question because, erase that, because the quotient will turn out to be isomorphic to sigma 1. But that's not the end of the story. In GIT theory, what we usually want is to write the quotients of, say, affine quotients as a spectrum of the invariant of the algebra of invariants inside our first algebra. So, moreover, this V1 GK, so it's in that case isomorphic to our first algebra, in which we have selected the invariance over GK. And if you want to find what are the generators of this ring of invariants, what you have to do is simply to use this equation here. It's a fact which is very easy to prove, is that the algebra of invariance inside when you have this picture is simply given by applying the former coordinates. So remember the ZJP to this reparametrization that was applied to any point inside V1 to get to our section. So, and this ring here I'm going to write that in somewhat formal way. So it's generated by, as I said, applying the coordinate ZJP to these expressions. So, namely, you do that. You take ZJ rho Z1 minus 1, you derivate it p times, and you take the value at 0. And here this holds for, say, g different from 1, and p, any p, actually. Okay, so let me give a name to these coordinates, because that will appear later in another form, actually. I'm going to call that lambda. Well, let me write it down. So definition, I call lambda p ij. So here I did the proof in the chart z1 prime different from 0. I'm going in my definition to go ahead and move to the chart vi. So I take zj rho z1 minus 1, derivative p times, and I take the value at 0. So you have to expand that to see really what it means. And if you do the computation, you will find many terms in this expression. But the first ones, the higher order ones, are given by, so here we'll have zj derivative p times. Might go wrong when I write that on Blackboard. So here you have, yeah, so these are of order 0 in any case. So zj derivative p times divided by z1 prime at order p. So here you see what it is very important that we are in the ring where we have localized things at zj prime, zi prime here, and we have minus zi derivative p times 0 primes p, zj prime, z1 prime. So here you see appear some sort of Wronskian at order p, and the rest are lower order terms. So this is an expression which lies in this localized algebra, and they generate the rings of invariance after we have localized at z1 prime. So we have here the condition j different from I, and p larger than. Okay, so that's why we have a geometry quotient on the regular locus, and somehow in the Bérczi-Kirwan construction, the idea is that they are able to extend this construction to another space rather than this space of regular jet differentials, which I'm going to introduce in a minute. But just let me write the moral down. So let me call Bj this quotient, Bj divided by Gk. So then what we have seen is that this regular locus would be simply the union of these affine charts. But this union is not a projective manifold. So it has a morphism toward X, but this is not a projective morphism. This is an open subset of a compact fiction you would like to have. So what we would like to do is to compactify that space. So let me write that Bérczi gave a candidate, constructed the so-called Bérczi sample jet spaces, which are candidates for compactifying these spaces, and that's the one that were used in Bérczi-Kirwan's proof of Green-Griffith length for hypersurfaces. But here, the space that was constructed by Bérczi-Kirwan is a different compactification of that space, and I'm going to, in the rest of this talk, I'm going to explain you how they construct that space. So let's move on to their construction then. So again, I'm not a specialist of non-reductive GIT, so I'm sometimes going to introduce objects without maybe properly motivating them. So if you bear with me, maybe you will understand that we get compactification of that space, but maybe I will not give the proper names for all the objects I'm going to introduce, neither the proper notation. So the notation I'm going to use is not the same as their original article. So first of all, yeah, I can say that orally. But what we would like to do is to quotient the space JK by, say, the unipotent radical first. So write that down, JK. And here there is a first obstacle, because this UK here has some points with a non-trivial stabilizer, namely the zero jets. And so we are in a situation where, if you use their terminology, semi-stability does not equal stability, and we have to perform a first modification to the space JK, and that's the definition I'm introducing now. I'm going to call BKX, so B as blow up, the blowing up at the zero section of JKX. So here I write simply 0 for the set of all zero jets. Zero section. Okay, so perform that blow up and call the resulting set BKX. So now we have a list of several facts about this BKX. So first of all, what do you obtain as an exceptional divisor? Well, you have to look at the tangent bundle inside JKX to the zero section, so normal bundle rather, normal bundle to the zero section inside GKX. So the zero section identifies with X. You have a JKX here, the zero section X here, and you want to understand what its normal bundle as a bundle over X is, and it is simply the sum of copies of the tangent bundle up to order K. Okay, so the exceptional divisor other than the projectivized bundle over X of X. It's isomorphic to that space. Alright, so you have that. And also, there is a natural action. So the action of JK on the space of jet extends to the space BKX. Quite easy to see. And what will be relevant for us in a minute is what this action is on the exceptional divisor. More precisely, what the action of C star lying inside JK on E. So pick lambda in C star. If you have a vector in E, by this description, at least fiber-wise, you can write it as a homogeneous element of the projectivized bundle here, with elements given by vectors in the tangent space, 1 to k, and you make act lambda on it, and you get lambda times v1, lambda squared times v2, lambda k times vk. So it's a weighted action with weights 1 to k. Okay, and now definition. I'm going to introduce a central object in the Bérczi-Kirwan construction. I introduce the set Z-mean, which is inside the exceptional divisor the part where the weight is minimum. So, what is it? Well, inside this projective space, it is simply the projectivized bundle obtained by taking only the first part of this decomposition, only the V1 and 0 for all the rest. So take 0 after the first step. Of course, this is isomorphic to the projectivized tangent bundle above X. And here, let me just introduce some piece of notation which I'm going to use all the time. Let me call that space X1. The first stage of the jet tower, actually. Okay, so you have this space Z-mean, which turns out to be isomorphic to that space lying inside E. Sorry, I maybe should have introduced that first. Another thing you can define on this blowing up is some sort of projection towards the exceptional divisor. I will call that P. So it goes from bkx to E. You take a point inside and to obtain a point in the exceptional divisor, you just have to take this the action of actually C star on bkx, and you take the limit as L goes to 0 of lambda acting on V. This lies in V. In 30 seconds, I'm going to write that down in coordinates. You will see that it is very easy. And just after introducing that space Z-mean, I wanted to define, and for that I needed actually this. We define the open set U-mean inside BK. Well, this is the set of points, so it's simply the inverse image of Z inside BKX. Okay, and this is the open set, actually, which will turn out to admit a geometric quotient by the action of the reparametrization, or at least its unipotent radical. So, fact, maybe it's not obvious here, but you mean inside PKX is a Zariski open set. So I'm going to give a few details because it will, so you will see it's very easy, but it will allow to fix a little bit the ideas. So to prove that, I will express in coordinates this morphism P. Proof? Okay, just checking the time. Right. So I'm going to write that down in coordinates. So maybe. Well, maybe I will not need coordinates explicitly on X, but just fix some small open subset inside X on which maybe after having fixed coordinates, you are able to identify jkx to the sum of the tangent bundle over it. So I've told you before that jkx is not a vector bundle on X. But on small charts, you can identify by simply taking all the derivatives, the kth derivatives. You can somewhat formally see them as vector. I'm doing that because I don't want to introduce coordinates and I want to write things in a consistent way using this notation. Then, if you write the blowing up, BKU, you can write it down simply by taking the standard operation of blowing up as the set of couples V1 up to Vk and say J1 up to Jk. The first one, of course, belonging to this projectivized bundle, and the second one to jkx, but on use seen as a sum of copies of tangent vector bundles over you. And here, of course, you have, say, V is parallel to J. And so on your chart, you can define the blowing up that way. Well, you have to be careful to what happens when you change charts, because the operations that permit to change coordinates on jkx are not linear. But at least locally you can define that, and what makes things work is simply the fact that the blowing up is an intrinsic operation. So once you know this space exists, you are perfectly allowed to describe it locally in that way, even though this is not really intrinsic. Okay, and so what happens to this action? So if I make lambda act on this couple, all right, so I have the weights 1 up to k, but this is homogeneous. So this is actually equal to V1. So I should have written lambda, but I'm simplifying everywhere. Lambda to the power 1 V2 up to lambda k minus 1 Vk. And similarly for the rest. Lambda k, jk. And so if I take the limits as lambda goes to 0, what do I find? I find a couple again. On the second part, I have, of course, 0. And what do I have for the first one? Well, actually, you will get a non-zero vector with 0 everywhere, except at the first stage, at the first step, where Vi is different from 0. Vi here. And this is the smallest I, such that Vi is non-zero. Okay, so if I take now the inverse image of the mean, I simplify, then U mean is the set of couples like that, which are parallel and such that V1 is independent. Okay, so this you mean is an open subset in the blowing up, and in the last 5 minutes I'm going to explain to you why it admits a good question by the action of UK first. Okay, so this is not relevant for the problem. Okay. Okay, so maybe let me give you a little bit more facts. So I have this morphism P, which started from BK and was going to E. If I restrict it to U mean, I find a morphism toward X1, which of course is given by the projection of all this to the VI. the V1, which is non-zero. And also, you mean, in the standard charts for the blowing up, you can write it as locally over X, say, as the spectrum of some algebra. So when you do a blowing up, usually if you want to write what are the standard affine charts, you pick the coordinates one by one, and you do things like that. Say if you want to blow up the algebra AB at the origin, you will have two charts, one given by that, and the other one given by the rational coordinates B A over B. So here, if you want to look only at the charts where you land inside U-mean, you see that you have to do that, but only with the denominators taken as the first order derivatives of the Zj, because they are given by the charts where you have formally inverted, say, only the first derivative in these jets, the jets inside Jk. So this will turn out to give the union from J going to from 1 to n of the spectra of the algebras, where you take as the coordinate giving the exceptional divisor Zj prime, and for the rest you put rational expressions with denominators given by Zj prime, and on top you use the standard coordinates. Here, you take all of these for L. Sorry, here there is no restriction, but JP is different. LP is different from J. Okay, does that convince you that you can write the U-mean as the union of all these spectra? So, if you compare to the picture of before, I had written a space JK reg as a union of spectra where I localized this algebra at Zj prime. Here I take a smaller algebra inside that, and the claim is that on each of these charts you also have a geometric quotient, at least something with the action of UK. So maybe let me call that open set WJ and theorem, say. The action of UK and WJ has a geometric quotient. Okay, so the proof is basically the same. And I'm just going to give you the invariants that generate the ring of invariants under the action of U. So same proof, say. And this time we find that the quotient Wj by, so here I'm taking for only the quotient by UK. In the first time. So before we had the quotient of the localized algebra, well, a spectrum of the localized algebra at Zi prime that was generated by all these things. But as you can see, these do not belong to this blown up algebra. So what you just have to do is to multiply them by the correct power of Z1 prime. So let me define psi Pij as Z1 prime to the power P minus 1 times the former lambda P Ij. If I do that, I claim that we have these charts which are given by spectra. So these things Pij. And, sorry, maybe let me write it only for W. With the restriction Pj different from 1, 1. And here I'm forgetting the coordinate Z1. Okay, so you have a full set of invariants which give you a union of affine charts. And to complete the geometric picture, I'm just going to say, and I will finish the rest tomorrow, that on each of these charts, you can define the projection P towards x1. So P going from W1 to UK towards x1 is given by forgetting all these coordinates where you have P larger than 2, because here, if you have P1j, if I put the first derivative here, I simplify Zj prime over Z1 prime. So forgetting the higher, forgetting the higher order derivative gives you the projection. And what I'm going to explain tomorrow is that you can define an algebra, a sheaf of algebras on x1 using these elements, such that when you projectivize it, you get the Bérczi-Kirwan space. And it is endowed with the tautological line bundle, and I'm going to explain you more details about that tomorrow. Thank you.
Questions?
Yep.
I mean, you probably talk about this tomorrow, but do you have any intuition for why this space has better positivity properties? Like what? Why does
So yeah, there are. I think the main reason for that is that, as it will turn out tomorrow, this construction is not an inductive process. So I explained that to obtain the space which is given by gluing, so not these charts, but the quotients of these C stars, say, you will glue all of them together to get some projectivized object above x1, and this is done in only one stage. And somehow, if you remember in the Maillet sample tower, you have to perform multiple projectivization at each step, and at each step you lose some positivity. Here, the object you get, I hope to have the time to explain that tomorrow, but it has a deformation to some standard objects on x1, which somehow have lost positivity, but only because of the first step. And I think, yeah, this is the basic idea. And one of the most relevant facts is that once you want to prove bigness of the tautological object on this quotient, you want to apply the Maillet's holomorphic Morse inequalities, the version of Siu Strapani, the algebraic version. So you want to write, say, this tautological line bundle as a difference of two net line bundles. And so typically what you do is that you pull back something from the base to write A, and you remove it immediately. And here you have to put some twists, so they give OX2 in the article. And the fact that here you have a twist which does not depend on n, somehow comes the fact that the only place where you can lose positivity is at the first step. And after that, you have a way of constructing immediately the object by taking algebras that live on x1, and which can have maybe, depending on the algebra you projectivize, so that's maybe something I should tell. Tomorrow, I will give the object as a projectivized algebra, so it will have a tautological line bundle, a natural one. I must warn you that it might not be exactly the same as in the article, but because it's not constructed in the same manner exactly. So there might be a twist that you need to take at the first stage to get to their tautological line bundle, which they call O1GIT. But up to this minor difference, the idea is basically that this O1GIT can be obtained by taking objects that exist on this X1 immediately somehow.
Other questions? No? Okay, so we can thank